all the sequences of sub-outcomes that you perform by following these lines from left to right. So what I'm doing is I'm spelling out one particular outcome in the sample space. So if you took this ordered tuple that has omega 1, omega 2, omega 3, omega 4, this would be an outcome in this entire sample space. Okay? So it's a string of sub-outcomes. So if you go here, 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 and that's an outcome in this sample space. So each of these ways that you can follow, so you take this block, this block, this block, and then whatever you do here, that would be an outcome in the sample space. Okay? So you'll have some tree diagram like this. Okay? And then, so each of these places where the tree diagram branches out, this is like a sub-experiment. So initially you'll have this first step, and this first step will have these outcomes. So this will be a sub-experiment, and so you can define, this will be a sub, like this here, these three, this is like a sub-sample space, and you can define a probability function on the sample space. So you could have like this group here, so you call this, let's call this thing omega sub 1, and I'll put this omega naught here. So, like this. And then the second one here, this one in green, let's call this omega, so let's do it here. Let me do it here in this column. Let's call this thing call it omega sub 2, and then up here I'll put omega naught, and then omega 1. And then this thing here, let's call this omega 3, and then I'll have omega naught, omega 1, omega 2 here. So these crazy omegas with all this decoration, these omegas are these sub-sample spaces. So here you'll have an experiment, and this will be a sample space. And then if this outcome occurred in the first step, then you'd have this new experiment, and this would be the sample space. Okay? So you can think of this as, this is the sample space, the second step, given that these two events have occurred in the previous steps. So this first omega is omega 1 raised to the omega naught. This is like the consequences, all the possible consequences of omega naught. And then this here, this is all the consequences of omega 1 if omega naught. So if you go omega naught and then omega 1, then you're looking at all the consequences that could come after omega 1. So these are the possible consequences of omega 1. And then this last one, this would be on the third step. These are the possible consequences of omega 2 if these ones happened before. So here are all the consequences of omega 2, right? So you'll have these sub-sample spaces, and then say you have, let's say you have probability functions. On each of these sub-sample spaces. So we have, say it's P1 omega naught. This is a probability function on omega 1 omega naught. We have a probability function P2 omega naught omega 1 on this omega 2 omega naught omega 1. We have another probability function on the next one. And you'll have like this. So what's happening is you have this compound experiment, and this compound experiment consists of these sub-experiments. So for each sub-experiment, you can think of this as the sample space, and then you can have some probability function defined on the sample space. So for this first sample space, I've defined someone's given me this probability function P1 omega naught. So that's a probability function on this sample space. This P2 raised to the omega naught omega 1, that's a probability function on this sample space. And then this P3 raised to these three things, that's a probability function on this sample space. Okay. So what I'm going to do is I'm going to define, so I have probability functions defined on each of these sub-sample spaces. I'm going to define a probability function on this entire sample space based off of these probability functions. It's going to be called the compound probability function. Okay. So you define a probability function P on the sample space of the compound experiment by this. So I'm going to define this probability function on this entire sample space. So the outcomes in this sample space, they're these strings of sub-outcomes. So let me just define the probability of an arbitrary string in this compound experiment. So you have this set that consists of this one string, so let's say it's omega 1, omega 2, omega 3, up to omega k. Okay. So I want the probability of just this string occurring. Okay. So if you want the probability of just this string occurring, you need to find this to be, you take the first probability function and you use the first probability function here, and you find the probability that this event will occur in this experiment. So you take P1 omega naught of this outcome, and then you multiply this through by all the rest. So you take the second probability function, the probability that this event occurs. So this would be omega naught, omega 1, omega 2 here, and then keep multiplying this through. So you'll have you'll eventually end up with this probability k of omega naught, omega 1, omega 2, up to omega k minus 1 of this last outcome. This is really not that bad. Let me show you an example of this. So what you're doing is, if you want to find the probability of the string of sub-outcomes, so that's the string of sub-outcomes is an outcome in this entire sample space of the compound experiment. So if you want to find the probability of this individual string, then you just take the probability function you have defined on this sample space, you take that, the probability of this event occurring, times the probability of this event occurring in this sample space, times the probability of this event occurring in this sample space. Do like this. So let's say you so there's an urn. It has red ball, a green ball, and a blue ball. Okay, so you cast a die. If the number is 6, you flip the coin. If the number, sorry, say the number is not 6. If the number is not 6. As the number is 6, then you choose a ball from the urn. So draw the tree diagram for this. So you're going to roll a die, and then depending on what the outcome of the die roll is, you'll do 2 different things. So look at this. You'll have these outcomes first. The first sub-experiment is to roll this die. So you roll this die. If the number is not 6, you flip the coin. So for each of these numbers it's not 6, the next step would be to flip the coin. Like this. And then if the number is 6, then you would pick one of these colors. So if the number is 6, then you have 3 outcomes now. Like this. Let me extend this and break it down. So, if you look at this first experiment, so just imagine, like forget all this stuff over here, just imagine I'm going to roll a die. So what's the probability that you get a 1? 1 out of 6. What's the probability that you get 2? 1 out of 6. So all these things are 1 out of 6. So you write these probabilities above these lines. So this number I'm writing on this line, that's the probability of getting a 1. Okay. And this would be the probability of getting 2, and so on. Now, disregard all this first stuff now, and just look at this experiment where you're tossing a coin. So if you're just tossing a coin, just imagine all this other stuff is gone. I'm just tossing a coin. So what's the probability of its heads? 1/2. What's the probability of its tails? 1/2. So each of these will have 1/2, 1/2 here. 1/2. 1/2. So now consider, just disregard all this other stuff. Just imagine you're going to draw a ball from this urn. So what's the probability that it's red? 1/3. What's the probability it's green? 1/3. This is all 1/3.